All right, welcome back, everyone. Let's get started. Please take your seat. Our next speaker will be Sean Gryb, who will be giving a talk with the title "The Shape of Past and Future," slight difference from the way it was announced in the program. So please, Sean.
Yeah, is this working now? No, have to hold it harder. Is it working now?
Yep.
Okay. No. Yes?
No.
Do I have to hold it the whole time?
Try again.
Yeah?
Is it not working yet?
I'll just use this one then.
Okay.
Use this one. All right. Now you can hear me. Okay. They're both working. Okay. So now it's, oh yeah. Okay, well, I'm really first delighted to be here. Thanks for the invitation. It's really been a great conference, and everybody has been interesting to talk to, also really delightful and kind and beneficial. So it's been a really great experience so far. Let me tell you a little bit about this work I've been thinking about for a while. So it started, I should say that a lot of these ideas are kind of inspired by and motivated by some thinkings of people like Julian Barber and collaborators, Tim Kozlowski, Fabio Marcati, and other people. My version of these ideas is a little bit different, so keep that in mind as well. It started with a paper with David Sloan, and then I've been working for about 5 years on a thesis that will have most of the details of these ideas. So I'm really hoping that I can walk you through the basic ideas, but at the moment the thesis is like almost 300 pages, and so obviously I'll have to shorten some of the arguments. I'm also working on a paper with Simon Friedrich about the arrow of time, and those have been input from all these other people. So lots of thanks for all of these people to go into this. I'm just going to start the talk with a very, I think, relatively simple philosophical observation. I kind of hope that somebody will one day say, oh no, this has been said by somebody way before, and I think it probably should be fairly maybe obvious to all of you, I don't know. But here's the idea, is that the measures that you use in a theory, the way you count possibilities in a theory, affect what the theory decides is likely. And that has a big effect on the inferences and explanations that you can make within the theory. So let me just kind of give you an example to show what I mean by this. So think about one kind of explanation, contrastive explanation. So here, contrastive explanations take the form something like if A, then B rather than C. So B is the exponendum, it's the thing, the question you want explained, why B. A is then the exponens is the answer, and C is the contrast class. And the key thing here is that often we kind of forget about the contrast class, even though it plays a very important role in the way that the explanation works. So why is A the likely explanation of B? Because it makes A more likely compared to what you think might otherwise have happened. Okay? And so, yeah, if A happens, okay, good. So the point is that the strength of the explanation depends on the way that the theory computes or assigns the conditional probabilities B given A or C versus given not A, right? So you might have some intuitions that the typical state in the universe should be time symmetric, but it isn't. We look around and we see loads of asymmetry in the world. Then you may say, okay, if I postulate initial state that is low entropy, that will explain why we see loads of time asymmetric states, rather than the thing that we thought would be likely to happen by random chance. Okay? Good. Now, here's the observation, which is that symmetries can put very strong constraints on the way you count possibilities. Okay? So gauge symmetries in particular, but they don't even have to be gauge symmetries. So examples of this, the philosophers might and some physicists might recognize Gain's principle of maximum entropy, where you try to constrain the kind of measures that you have in theory by using the symmetries to limit it to something unique or somewhat unique. Also, gauge invariance in path integrals. So a guiding principle in particle physics is often anomaly cancellation. So, and one way to think about anomaly cancellation in terms of the path integral is, when you regularize the path integral to do calculations, you break the gauge invariance. What you want to do is try to set that up so that when you remove the regularization, that gauge invariance is maintained. And the basic idea here is you don't want to either count two states that are physically indiscernible more than once. You don't want to overcount indiscernible states. But you certainly don't want to assign different probabilities or different likelihoods to states that are related by a symmetry. Okay, that's the idea. Oops. Right. So here's an example. I skipped the point. So the point is that, okay, now that you have these constraints will affect the measures that you use, the way you count possibilities, and then through what I just said before, that can have a big effect on the kinds of explanations and inferences you make. So an example here is, okay, if I decide, or if I want to have a theory where Lorentz invariance is a symmetry rather than Galilean invariance, then the way that I interpret what happens in interferometer experiments is very different. In one case, I might, in the case where I think Galilean symmetry is the symmetry, then I might need to postulate an ether and think about how the ether compresses objects in different ways. If I think that Lorentz invariance is the symmetry, then I don't need to do all of that. I don't need the ether at all, and I can, have a completely different kind of explanatory structure for the same experiment. Okay, so good. Now, the next step is to argue that cosmology has a symmetry. And I'm going to make the claim, I'm going to try to argue to convince you that that symmetry should be treated as a gauge symmetry. Okay? So it's not a symmetry that's unfamiliar to cosmologists. It's just a statement that scale, the absolute size of the universe, is not directly observable. It's not a controversial statement. On the other hand, the rate of change of the absolute size, that's the redshift, that is directly observable. We can look at how light redshifts from different periods. So now, this is because, and I'll discuss exactly how this works a bit later, but that's because cosmological models are invariant under a particular symmetry. It's called dynamical similarity. All right. Now, my claim is going to be that we should think about dynamical similarity as a gauge symmetry. We should treat it that way. We shouldn't count states twice or that are related by dynamical similarity. So two universes that differ only by their absolute size should be counted the same, or shouldn't be overcounted. They should be counted as the same state. And doing this puts strong constraints on the kinds of measures that we want to use when counting possibilities in cosmology. And in particular, if you use a measure that is dynamically similar, you will get very different intuitions for explanations about the arrow of time. Okay. So I hope that logic is clear. Let me now try to give you an idea of why that is. Why is dynamical similarity particularly relevant for the problem or explanations about the arrow of time? And the reason is because, the standard Liouville measure, the standard way that we count possibilities in physics usually, is the Liouville measure, and it's time independent. And this is actually, in some ways, really central to the problem of the arrow of time, because you say, if I count possibilities using the Liouville measure is time independent. But time independent measures, you don't expect to put high weight on solutions that are highly time asymmetric. So then you get this kind of intuitive result, but formally you can make it more rigorous, that solutions that are highly time asymmetric will have low weight according to the Liouville measure. And then you have a problem because our universe is then seemingly low weight relative to this measure that we always use. The thing is that the Liouville measure is not dynamically similar. So the Liouville measure attributes different likelihoods to states that are related by dynamical similarities. So if you want to treat it as a gauge symmetry, then you can't use the Liouville measure. You shouldn't use the Liouville measure anymore. And basically, the reason why this happens is because of what I said. The symmetry involves weighting a variable and its momentum differently, so that I say that this scale factor, the absolute size, is not measurable, but its time derivative is. And these are conjugate variables. That means that the symmetry acts differently on Q than it does on P. And that ruins, that just changes the Liouville measure when you act with it. So, okay. If I really want to think that dynamical similarity is a gauge symmetry of cosmology, then I'm in this situation where now I can't use the Liouville measure, and it turns out there's no natural time-independent measure that you can use anymore for cosmology. Instead, the natural measures that are invariant are highly time-dependent, and they're peaked at smooth states at early times. So what I'm going to claim is that if you're a late time observer and you are counting possibilities using these new class of measures, what you will find is that the past states have very large redshifts generically. So we look into the past, and not just typical states, but generically what we see is highly redshifted universes. And also, we typically see much smoother states. In fact, we see smooth states as typical. Okay, so that's a pretty strong claim, and I'm going to try to defend it. Hopefully, that will come all the way at the end. Hopefully, there will be time, but I'll probably have to skip some of the details. Okay. So, if all of that is true, if you buy this, then you say, well, this is maybe a promising way to think about the arrow of time. Okay, so so that's the roadmap. That's where I want to take you. I don't expect anybody to believe what I say so far. Hopefully by the end you will still probably not believe me, but maybe a little bit better than now. All right, so what's the problem I want to solve? I think a good way to, I think this is important because when we talk about the problem of arrow of time, it can mean lots of different things. So I want to be very clear about the specific problems I'm interested in solving. And I want to start with Price because he's a pretty good guy to start with. I think he did a decent job of characterizing the problem because he focused in the way that I want to on like the empirical problems that we actually are worried about solving, not the metaphysical problem of like does time have a direction. So in particular, he points out in his paper that there exists a large numerical imbalance in at least one quantity, often the entropy, that describes process in time, and this leads to a persistent temporal gradient across the known universe. So what's significant is the fact that there is this large numerical gradient in a quantity, which is people usually call it entropy, and that gradient is not just very significant, it's also persistent across all of space. So it's not that like processes go in time with one arrow of time here, and on Alpha Centauri they have a different arrow of time. Everywhere that we see, as far as we can tell, stars supernova only in one way. Okay, that's a mystery because this large numerical imbalance doesn't seem to be encoded in the laws of physics. We don't really get this big numerical imbalance when we look at the laws of physics. That's the claim. So this is a problem because we would like to be able to explain this despite the near time asymmetry of the laws. I put near because actually the laws are not time symmetric. There's electroweak symmetry breaking. It's not time reversal invariant, but that doesn't generate enough time asymmetry to explain these numerical imbalances that I'm talking about. Okay. All right, so what are those numerical imbalances specifically? Okay. And I think that's also going to be important to talk. What specific processes am I trying to time asymmetric processes am I trying to describe? And Price, in his paper, focused on one, and I think he got the idea mostly from Roger Penrose, maybe other people. And this is that this question of why was the matter in the early universe so smooth? Why was it in such a low entropy state? Okay, and Penrose's original argument goes something like, well, what would we expect the universe to look like if we just counted states? What's the most likely state of the universe according to quantum gravity? And then he said, well, we should be in some kind of gravitational equilibrium. That would be the most likely state. It's the highest entropy state. And then we expect it to saturate the Bekenstein bound. Okay, so whatever, the number of states proportional to like the area of the Hubble horizon or something. Then Roger Penrose goes through the calculation, is a little sketchy, maybe pretty hand-wavy, but the conclusion is something that the universe that we see is 10 to the 10 to the 123 times less likely than this typical state here. And so he says, well, you know, there could be some problems with my argument, but this number is so huge that it tells us that like the world is very different from the way we would expect it to be based on these counting arguments. Okay? And that is, and moreover, he also says that if we can explain the smoothness of the CMB, then we're basically done because we have this low entropy initial state, and then gravity will naturally clump everything. And that will mean that if we start in a low entropy state, gravity will want to clump everything, and that clumping gives us a directedness. Okay, so gravity's natural tendency to clump states that are smooth is going to lead us to all the kind of time asymmetry that we now see on Earth. Okay, so I'm going to say that this is definitely a puzzle. It's definitely something that I want to solve, but it's neither the only puzzle nor the most numerically significant one. Okay, and for this I have to thank Carlo Ravelli and also David Wallace. There's a second problem that I'm interested in solving here, and this is what I call the redshift problem. So the way I state it is, why was the redshift so violently large and monotonic in the past? Okay, and I think the real mystery is not just the violence of the redshift, but also the monotonicity of it, steadily going down. It started very high and has steadily gone down. So what Wallace and then later Carlo picked up on is that, when the universe expands, it starts to cool, but it cools faster than the matter has time to equilibrate, to reach equilibrium. So in particular, you get these freeze-out moments. Okay, so one example, and the one that he focused on, I think Wallace focused on, was the Big Bang nuclear synthesis. So if the universe hadn't been expanding, Big Bang nuclear synthesis would have continued until it reached equilibrium, until all the atoms were iron, I guess. And then if that had happened, we never would have had stars because there would have been no nuclear synthesis, since there would have been no hydrogen left to bind together to form helium to make the stars that we have. And so what they argue here is that the kind of entropy stored by these freeze-out moments is much higher than the entropy you get from gravitational clumping. So that what the clumping does, you can think of it as a catalyst. As like stars start to clump, then stars start to collapse, and then nuclear synthesis starts in the stars, and that's what releases all this trapped entropy. Okay. So, but in order for that entropy to have gotten trapped, they argue that, well, the universe needed to be expanding very quickly and violently early on. Otherwise, it wouldn't have happened. Okay, I think this is a problem. I want to explain this. But I also want to say that, like, in order for that argument to work, you need to assume homogeneity and isotropy just so that you can define entropy in the universe, because you use periodic boundary conditions, stuff like that. So, you know, this argument is a good one, is important, but also you still need to explain the smoothness. Otherwise, you can't even apply this argument in the first place. So really, I want to do both. I'm going to be worried about both. Okay? All right. How much time do I have, Chris? A lot, eh? Okay. 15 minutes. 15. Oh, okay. Good. So I'll skip through this because I think this is because I want to set up a kind of, I want to say, well, why am I even worried about solving the problem of the arrow of time? It's because the solutions that we do have are not satisfactory to everybody. So Price talks about two different approaches. One is you can posit a particular fact, the past hypothesis, or you can just posit a times asymmetric law, so something like the GRW collapse theories. This is like two different ways that people follow to try to solve the problem of the arrow of time. But what Price points out here is that actually the generalists have like a redundancy problem, that they both need to, they have this time asymmetric law, but they still need to explain the smooth initial state. So in doing that, they just have to kind of explain the past hypothesis anyway. And so whatever work they're doing to do that, they're kind of doing double work. On the other hand, people like John Ehrman and many others, okay, have argued that the past hypothesis itself is ill-defined, ambiguous, it's not explanatory, not even false, is the title of John Ehrman's paper. I think it's just, I won't go into detail, but it summarizes the kind of feeling that people have about the past hypothesis. Okay? And so now you're kind of stuck because neither one of these is particularly nice. Okay? Even if a large part of the community might favor the past hypothesis anyway. Now I want to suggest something completely different from both of these. It's not generalist or particularist. It's a proposal where the time asymmetry is broken, so the laws are going to be time symmetric, and I'm not going to have to postulate a past hypothesis. The way that time asymmetry is introduced is because observers who are close to, who have a relationship to certain geometric structures in the space of solutions, see an arrow of time. Okay. Let me talk about that later. So the roadmap is, I'm first going to tell you why I think dynamic symmetry should be treated as a gauge symmetry. Then I'm going to tell you how to treat it as a gauge symmetry, and how that's different from most gauge symmetries. And then I'm going to give you the proposal and explain. I'll talk about two models, and then I don't know if I'll have time to go into the details of these models, unfortunately, but the models are supposed to individually solve the smoothness and flatness problem. Okay, I just set up. So how do you find a gauge symmetry? Okay. So my argument relies on treating dynamical similarity as a gauge symmetry, so I need to really explain why I think it should be a gauge symmetry. And that means I need to tell you what I think a gauge symmetry is. And the slogan is going to be kind of inspired by Dirac, the idea being that the underdeterminations of equations of motion should be matched to underdeterminations of representations by phenomena. So there's a should here. It's a normative statement that when we're setting up theories, we want the underdetermination of our theories to match the way in which our representations are underrepresenting the phenomena. Okay? I'll be a little bit more clear in a second. So this is kind of very similar to Dirac. Okay? He had a proposal. If you know about this, then that's great. If you don't, all you need to know is that Dirac made a precise proposal for how to identify the observables in like a typical gauge theory. And that proposal is quite specific, but it only applies to theories that are Hamiltonian theories. They're described by Hamiltonian, and my theory will not be a theory like that, so I need to generalize this. He also equivocates between representations of the world and the world itself. Physicists tend to do this. They tend to say that space-time is a Lorentzian manifold. They actually mean as if like a Lorentzian manifold is something in the world and not something that we're using to represent stuff in the world. So I wanted to be a bit careful about that. And in that sense, I'm inspired by Colton, who had this proposal for what he called analytic symmetries, and for all intensive purposes, these are gauge symmetries. Okay? And his idea is just, if you have a theory, you try to reduce the gauge symmetries until you can't preserve empirical content anymore. So you try to take out as much structure as you can until you've taken out too much that you can't describe phenomena anymore, and then you're done. But he didn't give any like procedure for how to do that. And so what I want to do is just kind of, what we did is just combine the two. So combine Dirac's kind of concrete dynamical intuition with this like procedure. Okay. So let me just tell you kind of the answer. And I think hopefully it will be kind of obvious that what you should do is just, what we think you should do is just find the smallest observable algebra on which to project the equations of motion so that you can save the phenomena. Right? So it's the same idea of Colton, just specifically look for an observable algebra onto which you can project the equations of motion that allows you to describe what's happening in the world. And that could be context dependent, so that the same theory could be applied in different contexts. You could get a different answer for what the observable algebra should be. Yeah, okay. And you do that because you don't want to. Okay, so this gives you a norm right away. If you believe this, then you should require that any measure that you define on this space should be projectable onto A. So it should give the same weight to any states that differ only by structures that are not in the observable algebra. Okay. Now how do you find these things? So we have like two formal conditions that are kind of inspired by Dirac. First, you look at the equations of motion, and then you require that they be autonomous in A, so that we don't want the equations of motion to depend upon things that are outside of A. And the second thing is we want them to be one-to-one. So we want to be able to evolve the equations of motion using only the observable algebra and nothing else. You might not be able to do that in practice, but as long as you can do it in principle. So you can do this like a gauge fixing. Okay. And then we have two empirical criteria. So you want, once you have this, then you want it to be such that A is sufficient. It has enough structure to represent the world, but it doesn't have too much. And this is the one that I'm worried about in cosmology, right? So you might worry that if you have too much, if you have what you think is your observable algebra, but it actually has more structure than you need to represent things in the world, then this says you should cut out that extra structure. Okay. So let me give an example, right? The example is FLRW. So it's the one that I'm interested in, one of the ones I'm interested in. I think we've talked enough about cosmology to know now at this point that there's a scale factor and a Hubble constant, and then you could put scalar fields. So the phase space is 6-dimensional, but it depends on how many scalar fields you have, okay, kind of more. The point is that the Friedmann equations allow you to do everything, okay? The Friedmann equations are the evolution equations that you use to make predictions in cosmology. But the Friedmann equations don't contain A, okay? There's no A in the Friedmann equation at all. And in fact, whatever initial condition you put for A, you'll get the same answer for any observations. So it's a pretty simple thing. You say, well, why do we need A at all, right? Now, obviously, maybe somebody will say, well, H is actually A dot over A. Okay, yeah, but that's that's not A, right? So the point is that you can just forget about A, treat H only as the independent variable, find its evolution, and then you can still make all the predictions. So here, A is more serving as a kind of intellectual intuition pump for what's actually happening in the universe when you have the Hubble redshift. But it's not necessary for making predictions. And so the claim is, I'm happy for people to keep around A, but my claim is that when you're defining measures, the measures shouldn't depend upon it. They shouldn't give different weights to states that differ only by the value of A, because we can't discern those states in the real world.
How about if you include perturbations?
Yeah, that's another, well, in my second model, I'll touch on perturbations, but. So our PISA now will say, okay, the principle that I just laid out says you should think of, so the observable algebra is just this. It's the Hubble parameter plus the scalar fields and their velocities. That's what I need to make predictions, not A. And the point, and the symmetry is then just rescaling A, okay? It turns out that's the dynamical similarity in this system. And this space is odd dimensional, okay? yeah, clarifying question?
Kind of. Similar on the line of what Chris was saying regarding the missing.
Could you put the mic on?
Oh, right.
The missing of the scale factor, because of course you have H, but on the other side you need also the energy density, and the energy density depends on the volume of the universe, namely on the scale factor. So I think, is it really disappearing?
Yeah. I mean, you have to come up with some procedure for measuring phi, but of course, that procedure will not involve the scale factor, because we know in cosmology that you can put any value you want for A, the initial value of A. It's a convention. Right? It's just setting the units of the world. So whatever procedure you have to measure phi will not involve, well, A will ultimately drop out at the end of the day.
Okay, Sean, 5 minutes.
Yeah, okay, so let's unless it's really, yeah, 5 minutes. Okay, so, well, it's okay. What is dynamical similarity? It's a symmetry that involves rescaling the action. So if you have an action, you write it in this way. If these variables scale this way, so there's a Q, there's a P, and there's a T, then what happens is you can set it up so that this term rescales and that the Hamiltonian term rescales. And then this C just comes right out of the action, it preserves the solutions. So this is a very general symmetry that exists in lots of different theories. You don't always want to interpret it as a gauge symmetry, okay? But in this case, I want to. And I claim that what's interesting and different about that is that this, because of the way the dynamical similarity rescales this, okay, it rescales the symplectic form. Okay, so that's the Louisville, well, the Louisville measure is like the nth product of that thing. So the Louisville measure will rescale under dynamical similarity by necessity. And so if you remove dynamical similarity, what you get is not a symplectic manifold, it's called a contact manifold, and it has this odd dimensional structure here, where it has these Q's and P's, but it has this odd guy A, which is called the Gryb. It's related to the Gryb direction of the contact manifold. Okay, it's just this odd direction. Now, in FLRW, the Gryb direction in the coordinates I'm using is just the Hubble parameter. And, okay. And then the, instead of getting Hamilton's equations, you get Hamilton's equations for this system minus a piece that looks like this. And this looks like friction, okay? It's not exactly friction because you also have this term. And so the whole thing is time reversal invariant, but it's friction-like. And the friction, the amount of friction is this thing here, called the Gryb flow of the Hamiltonian. I call it the drag, because it's kind of like the drag coefficient in the friction theory. Okay, so in normal Hamiltonian theories, the Louisville measure is preserved, but in contact theories, the Louisville measure evolves, and it evolves in this particular way. The drag is like the focusing factor of the measure. Okay. So if the drag is positive, then the measure will shrink, and the opposite. Okay, so my claim is that, yeah, this friction-like dynamics that you get when you remove the scale factor is the origin of all the time asymmetry. And the way that can work is, yeah, I got my 5 minutes about 4 minutes ago, right? So, yeah. I'll just draw a picture then. I think the picture will go easier. So the idea is when you have these systems with friction, you can get a lot of structures that you don't have when you have symplectic theories. And one of them is an attractor. So, oh, I'm going to have to do this. And this, I guess. Oh, is that okay? A, attractor. Okay. So you have some space. So the page is like the face space, the contact space. And then an attractor is just a point that all the dynamics goes to. So if you have solutions here, you start here, then you go into the attractor. And you go into the attractor asymptotically as t goes to infinity. There could be other attractors also. Okay, you could start here and you could go into a different point. That's the most general case. And what I want to, I think if I go back, oh no, I can't go back. So this is interesting because if you have an attractor, then it seems like you have some kind of time symmetry, but you need, well, okay. In these theories, there's also a second structure, okay, which is where the measure focusing factor, I have it on the other slide, but I can't get it right now, is 0. Okay, so there's a point along these solutions where the drag is 0, so that there's actually no friction instantaneously. And we call these points Janus surfaces, J. Okay, and the idea here is that you get an arrow of time, because the point is that there can be other attractors on the other side, okay, that go like this. That's because these solutions are ultimately time reversal invariant. But the time reversal invariance is broken here if you have an observer who's near one of these attractors and is now looking back toward the Janus surface. And so what happens is this mu naught is 0 here, and then it will get pulled toward the attractor. So there's a quantity which is like the distance along this curve. Sorry, I'm pointing at the distance along this curve, which is going to infinity as you get close to the attractor. And so that gives you the resources to have a large numerical imbalance that you can use to say, I'm now very different from where I was at the Janus point. Okay? So that's the basic idea. Do I have to delete this? Okay, this. Yeah. Okay. So that's the idea, and that's the picture. What? Oh, okay. So in dynamically similar theories, the drag itself is gives you the resources to have a measure that will be 0 at the attractor, a way to define this. So if you have something that is 0 on the attractor and then grows monotonically toward the, 0 at the what I call the Janus point, and then grows monotonically toward the attractor, then I can use that quantity to talk about numerical imbalances. Okay. So in the last minute, I'll talk about how this actually works in cosmology and then in the n-body problem. Okay. So yeah, actually, Faraz's talk was great for me because it set up a lot of what I need. I'm going to put even stronger, way stronger conditions than what he did. I'll take FLRW, I'll put a positive cosmological constant. All I have to assume is the weak energy condition, and I'll take k equals 0 for simplicity. And then it's just a theorem that the Hubble parameter is monotonically decreasing from the Big Bang all the way to the de Sitter attractor in this case. Okay? So that's somewhat familiar to you, hopefully, because of Faraz's talk. And so here's a case where I have a simple choice of laps tells me that the drag is just 1 over h. So 1 over h is infinity at the Big Bang. So this is 0. And then it grows monotonically to a constant at the de Sitter attractor. So it has the same properties as a non-equilibrium entropy function. Okay. And I claim this solves the redshift problem because if you're close to the de Sitter attractor, you see violently redshifting. You see that the Hubble parameter was much higher in the past, not just typically, but generically, okay, given all these assumptions. The smoothest problem is a bit harder. This is where we don't do a full perturbative analysis, but we're just looking now at the n-body problem and imagining redshift is not that important. Okay, eventually we want to couple that to an expanding background. But the question we want to ask is, why was the universe in a smooth state? And we want to use a model, an n-body model, with energy greater than 0. This is a model considered by Barber and collaborators. But I looked at this a lot more carefully to double-check their claims. This theory has a dynamical similarity, which is this is actually related to the Kepler's third law, okay? When you take n equals 2. And here, this rescaling of the overall size, we want to interpret as like scale factor. So The idea is that in the cosmological setting, we should think of this dynamical similarity as a gauge symmetry. If we do that, then we want to quotient by this dynamical similarity and find a contact system that will represent that dynamics. And we can do that. And what we find is that there is this quantity, which is basically the momentum. So I is like the natural size of the system, and d is its momentum. And this quantity happens to be monotonic, and it goes through 0 on a generic set of solutions. So when it is 0, we call that the Janus point. And when it goes to infinity, turns out the system has attractors. This is an old result from '76, but if you divide the coordinates by the average, like the typical lengths, you get like a scale invariant size. Then you find that as t goes to infinity, you get a constant. That's an attractor. The attractors are like, usually they're Kepler pairs, okay? But there can be any subsystem that grows smaller than t to the 1/3. Okay, so this is a realization of the more general thing I talked about, this Janus attractor scenario, where you have a Janus surface, you have an attractor, and then if you're close to the attractors, then you, well yeah, I should say that the attractors are like clumped things. Okay? The attractors are clumpy things, they're Kepler pairs, they're subsystems that are forming, right? And what's interesting about this is that you might ask, well, what is the measure that I'm using? Does this give high weight to smooth states? And the answer is yes. Okay, it does. And that's the short answer. The long answer, I don't have time for. But what I want to do is show some plots. This is a particular statistic that measures homogeneity. This is what happens to that statistic, the blue line, if I sample from a uniform distribution. So this is what I expect the statistic to look like for a completely smooth state, the definition of a smooth state. And the orange one is what I get from projecting the loop, so from constructing the natural measure for this theory. And what you can see is that they're not the same, but a typical state drawn from here could statistically have been drawn from this one. But that's only true at the Janus point. It's very important that this is what the distribution looks like at the Janus point. Once the dynamics turns on and the system starts to go, it starts to clump. And this distribution will start to move very far from this, okay? Of course, there are lots of way more clumpy states in the n-body problem than there are smooth states. But if you ask the question, how many smooth states are there at the Janus point? How many clump states are there at the Janus point? According to this method, the answer is almost none. Okay, so that's where the intuition gets flipped. The proposal is not a generalist proposal. The laws are time reversal invariant. It's not particularist because we haven't made a particular hypothesis about some fact about the world at some time. But we still get some kind of explanation of time asymmetry. Okay. I'm out, I'm done. If somebody wants to know about what we want to do next, then we'll talk about it in the discussion. Thanks.
Thank you very much. The commentator is Niels Linneman. Please, Niels.
Yeah, thank you very much, Sean. Very interesting. So you really offer an enticing account of a cosmic error of time in GR. So an error of time exhibited by the cosmical solution to GR. More generally, what I would like to really point out is how great it is that you kind of pull out the best of shape dynamics and make it available, so to speak, to non-shapers, right? I think this is the right move. So in addition to your work on the error of time, you and collaborators also have work, for instance, on singularity of resolution, which can be put to use like this, and so on and so forth. I think it's very good and very interesting to look at what you're doing. More generally also, I really applaud this kind of interesting framework you're setting up for symmetries, which can, among other things, also then account for dynamical similarities. And now we go over to two general comments / questions. One will be on the physicality of the scale symmetry, and the other one will be on the relevance of your cosmic error of time. So we just start with the physicality of scale symmetry. Maybe then you can respond. Then we go to the second block. Okay, about the physicality of scale symmetry. So your central take seems to be scale in cosmological solutions of GR is a dynamical symmetry, and furthermore, so over and above to this, gauge, right? And so the two questions arise. First of all, one thing that dynamical symmetry is just an artifact. I mean, solutions to GR are usually not scale invariant, right? Cosmological solutions have this somewhat macroscopic flair to them. I mean, think, for instance, that the perfect fluid is enforced by the typical symmetry assumption of cosmological series, isotropy and homogeneity. And yeah, a perfect fluid is a more or less high-level description you do for GR. And secondly, yeah, even if you buy into all of this, what is the underlying picture of cosmology one should have in order to regard dynamical symmetry as gauge? If I, for instance, take David Wallace in a recent paper, and his outlook on cosmology, I mean, first of all, he states that the most common applications of GR are to subsystems. He talks of pulses of gravitational radiation, Newton stars, and so on and so forth. But even for cosmological applications, he says that it's not clear to him why these models are not meant, as so to speak, for a certain observable sector of the universe, as opposed to for something hypothetically, infinite or whatever, holistic. So this is a different take on cosmology, of course. Would be just interested to hear from you about this. And maybe further, so to speak, isn't it that after all this kind of idea of scale symmetry as gauge is still backed up pretty much by this Poincaré/Barburian ideology of, I go to bed tonight and tomorrow the world might have been rescaled by 5 times and I wouldn't have noticed it. So just a question to you,
Okay, okay, let me try to think about it. So, when we used to, there's 2 different ways to try to motivate what I'm doing. One is to say, Poincaré made a good point about the scale, and that when you wake up, I mean, if at any moment the universe is changing its absolute size, and everything in the universe is really rescaling in the same way, that there's no observable difference. That's how we, in shape dynamics, often motivate this move toward taking scale and variance seriously. I don't think I have to do that, though. I think that I do buy that argument. I think it's plausible, it's nice, but I don't think that I have to, because I'd rather just say, do I need scale? Do I need the overall scale of the universe in order to make predictions? And so Wallace makes a good point about cosmology. I mean, you can still think of them as subsystems. Maybe there is a situation in which you might think of the scale factor as a useful, not just theoretical tool, but also as a quantity that has empirical content. Okay, I want to put some interpretation onto my scale factor that will allow me to explain real phenomena, and I think that's a perfectly possible thing that could happen. My claim is that that's not what cosmologists do. And so, for example, originally, if you really take scale invariance seriously, you might worry that the Hubble parameter should be gauged as well. But then you get into trouble because cosmologists do have a way of understanding the Hubble parameter in terms of redshifting of light rays. So if light was produced in a star, how many years ago, and it comes to us now, the same light produced under similar conditions should have the same wavelength, but it doesn't. And the difference is the redshift. Okay. Now, normally that's interpreted as, well, the light traveled through space and space expanded, and because of that, it got redshifted. Here, we don't need to think of it that way. So here, the idea is, well, there's energy loss, so there's friction. It's a frictional system. The light traveled through dragged across energy as it traveled through space. But the size of the universe doesn't really matter in that picture. And so you can use the intuition pump. I don't mind that, but when you start counting states of the universe, my claim is that it's wrong to count states that are related only by different choices of scale factor, because we really don't see that in observations. If we did, if we had a way to do that, then I would be also fine with that. It doesn't seem to be the case.
Okay. In the macroscopic nature, for instance, of the cosmological solutions, which you might take to be like an idealizing aspect, could this be a reason to, after all, be be doubtful about this apparent symmetries of,
and maybe this is related to Chris's question, not about introducing homogeneities, but introducing quantum fluctuations specifically. Because h bar has units of angular momentum, so it's actually going to be rescaled, part of my outlook, rescaled under quantum mechanics. So at the moment, I don't want to speculate too much. Here's the problem, right, is that the dynamical similarity is rescaled with Poisson brackets. So how do you quantize this theory? And still have this as a gauge theory at the quantum level. We regard that as an open problem. So again, you can take 2 points of view. One is, let's try it and see what we can do if we still explain the world. What new things can we explain? In the classical theory, I claim that you can gain explanatory power by explaining things like the arrow of time. Maybe something similar happens in the quantum theory. We don't know, right? Maybe we try to implement this as a gauge symmetry at the quantum level and we get garbage. Then we're in trouble, right? But our intuition is that the Planck constant that we use is a relative scale. We take the ratio between the size of the Bohr atom and other systems, and we compare that. We compare that ratio. And so I don't think it should be necessary to have h bar as like an absolute scale in the theory. We should be able to describe quantum mechanics using ratios in a universe where the scale factor is still gauge. But that's an open question, and I think it's exciting stuff to work on in the future.
Yeah, thank you. Let me get to block 2, so to speak.
Oh, shit, okay.
Yeah, sorry. On the relevance of this new cosmic arrow of time you're presenting. So there's an arrow of time for observers near an attractor with a Janus point, so to speak, in their past, right? And you can think of this arrow of time as being characterized by a measure shrinking. And now, how does this arrow relate to expansion/contraction? I already cornered you about this somewhere, and you, I think, agreed that this kind of sense of arrow of time is associated to an expansion of time, right? So one could, expansion of the universe. So one could, after all, say when we
redshift.
Oh, you said redshift. Okay, sorry, redshift. Okay, so I could, after all, say you recharacterize the set of solutions which are associated to increasing redshift through this kind of measured picture, right? That's I think
that's right. So I mean, I'll use the intuition pump of the expanding universe, is what everyone's familiar with. But so part of what I did in my models, I put in conditions that would stop the universe from recollapsing.
Right.
Specifically, okay. If the universe if you allow conditions such that the universe can recollapse, then you don't have this Janus attractor scenario. But would you expect an arrow of time in such a universe, a well-defined arrow of time like the one that we have in such a universe? Should you expect that? Because once the universe recollapses, it's not really clear that the arrow of time will continue to hold in the way that it does. I don't know, right? All I know is that what I can say is that in these conditions, then you should be able to see this large numerical discrepancy.
Good. Okay.
But you could generalize this. It's not like a necessary condition for an arrow of time. It's certainly sufficient. So you could imagine like local arrows of time coming from periods of prolonged expansion or something.
Yeah. Okay. Then let me raise my question. So, can we really say then, though, that we don't need the path hypothesis anymore? I mean, you have this point about the behavior is so generic that the path hypothesis won't be required, right? I mean, if I think, for instance, of this picture of Wallace and Rovelli, for instance, then the idea is, a lot of work is done by the expansion, but this is always seen as a catalyst, so to speak, right, for entropic processes. And now what I'm more concretely wondering, yeah, you have a nice toy model, and for this you have this evolution towards a tractor. And of course, one can always cheaply attack a toy model for just being a toy model. I mean, of course, this is ongoing work, so I'm not going to do it in that sense, but I'm specifically wondering about, is this structure picture, so to speak, precise enough? Is it not somewhat crude to account for certain things with which we can actually, relative to which we can actually make a distinction using different path hypotheses? I mean, here's an example. David Wallace, for instance, states for the purely classical sector of the cosmos, path hypothesis, which is about an almost uniform terminal state, right? Just after just at the beginning of the transparency era of the universe, and this is then, so to speak, to account for also the fluctuations we see in the macroscopic fluctuations in the CMB. And so if you can take this kind of path hypothesis, which accounts for almost uniform terminal state, and compare it to a path hypothesis which doesn't make a difference. I mean, we just talked about a uniform terminal state. How would this, so to speak, be distinguished in your attractor picture? Would both scenarios lead at the end of the day into the same attractor, or would this be distinguished?
It should be almost the same. I mean, I guess what what I want to say is that using these net measures,
right,
if we count, then it looks like the past state is in these n-body problems is close to being smooth. That is very far from being able to describe the state of the CMB. But it goes against the usual intuition that people have about the n-body problem, where, like, you know, the idea is like, well, a typical state in the n-body problem is highly clumped, so that the smooth state would be unlikely. And that's true. That's true if you count all the states, even in this picture. But what's not true is that if you that it matters at what point along the trajectory you are for counting states. So if you're on a Janus point, there's a dynamical condition that knocks out all the clump states, makes them much less likely. So that the intuition is kind of like, it's not, you should, when you're counting states, you shouldn't just think of this in a timeless way, which is what the Liouville measure makes you want to do. It makes you want to say that counting should be independent of the time that you make the counting. Here, you're saying actually the time that the counting matters because the measure is time dependent. And if you put this Janus condition, then you'll see that all those clump states are suppressed. Now, what does that mean for like CMB? It's very far off, right? But what we want to do is come up with a model that combines both of these together and is, maybe say like, okay, the ideal thing would be, oh, look, here's the state of the CMB is likely, or let's say the state after inflation is likely under this measure, and then you don't need inflation, right? So the idea for introducing inflation is that, well, these conditions are very fine-tuned, but it could be that using these new measures in a more realistic model, that is no longer the case. So that would be the kind of hope. I think it's slightly different from your question, but
no. Very helpful. Yeah, thank you very much, Sean.
Thanks.
Chris.
Yeah, so thank you very much. I think so I have two questions, one which I expect the shape dynamics people have an answer to, and the other is a little bit more inchoate. But the first one is just, we all love the FLRW models, and I can see the case for identifying excess structure in the case of the FLRW models, but judgments of excess structure are very sensitive to exactly what model space you're looking at. And so this is a general worry that if I actually wanted to have a more generic cosmological model where the Hubble constant is really just an average of local expansion rates that vary from place to place, or if I want to include perturbations, my initial thought is the A's pop back in when you start looking at the more general solutions. And so is it your claim that there's still a dynamical similarity even in a more generic cosmological solution?
Yeah, so I think the answer is yes, I do think that. And the reason is because in cosmological perturbation theory, the perturbations are they're not dynamically coupled to the background. So the dynamics of the background is still determined by the Friedmann equation, and then you put the perturbations on top of that. So they ultimately don't depend on the scale factor either. I mean, they respond to the geometry, but they're not back reacting onto it. And I think that for that reason, you will get a dynamical similarity when you put perturbations.
Okay.
What would be, I think what's more of a question in my mind is what happens.
Quantum fluctuations.
Yeah, is when you include the quantum fluctuations, and because that will rely on a theory that we don't have. We don't know how to treat dynamical similarity at the quantum level yet, because it's dissipative quantum systems are tricky, and there's not one single way that people agree on how to quantize them. So I don't have the answer to the second question, but the idea would be that hopefully we can treat the h bar as a relative scale as well.
Yeah.
Okay, so
The more inchoate question, I expect Wayne would have a better way of posing this, which is just that there's a whole apparatus for thinking about measure theory and probability in dynamical systems where you have a dynamically invariant measure like the Liouville measure. And in some sense, I think you're sort of still using that apparatus now that you have a measure that is not time independent. And the question is it clear that that sort of way of thinking about probability measure just carries over to this new circumstance so that you can then interpret the measure as indicating that the typical state has a certain feature? It's just, as I said, it's sort of inchoate, but I think the way we think about measure and tied to probability is often for systems where you have a time-independent measure, and there's a lot that depends on the fact that it's time-independent.
That's a good question. I haven't really thought about it that way. We've just been assuming that you have to find a measure somewhere. But yeah, I think but it leads into a bigger point, which is how do you interpret these measures?
Right.
At the moment, we're using them because we're finding them because they're mathematically convenient.
Right, but then you're interpreting them in terms of telling you something about a typical early state.
Exactly. So we're interpreting them the same way. I'm not going to conjecture an answer right now, but that's a good point. Can you do that? The thing is that if you only need to rely on time-independent measures, that's the only way to interpret that sensible counting, then you're really in trouble here because I didn't say this explicitly, but you can construct time-independent measures. It's just they're highly fine-tuned to the dynamics, and they're on phase space, and they're super complicated. And that will be even worse in general relativity. You'll basically not even be able to find it explicitly, only implicitly. That would be really bad. I don't know how to do science that way. With a measure you can't even calculate.
Okay, Wayne.
Well, Chris read my mind. But yeah, I was going to ask you about the role of these measures. So you started your talk talking about measures as ways of counting possibilities, but several times in the talk, there was a implicit inference from counting possibilities to probabilities, and then at the end, to typicalities. So yeah, what's up with that? I guess I want to ask, what notion of probability is at play here? Yeah.
I was a bit cavalier in the talk because I was trying to explain more than I had time to explain.
Right.
But actually, what you get in these, what's actually interesting about these dynamically similar measures is that they give you, both for the FLRW models and for the n-body problem, is they give you probability measures. So they're normalizable. Yeah.
Right, but how am I supposed to think how am I supposed to interpret these probability measures? Now, it's a serious question because I think that there's something that's very damaging in these talks is the idea that there's a sensible notion of probability that is just a matter of counting states. And I think it leads to pseudo problems. So, for example, like if you think about the Liouville measure, okay, that's a time invariant measure. What's special about that? Why should we ever think that that gives us a probability measure? Well, I think the answer is, in statistical mechanics, is that if I start, for a whole host of systems, if I start with other measures, probability measures in the states, then they converge towards the Liouville measure, and hence that would be at least when restricted to macroscopic variables, and hence that's a rationale for using that for a system that's had time to equilibrate. I know of no argument whatsoever for taking the Liouville measure as being a probability for a system that hasn't had time to equilibrate. And this is an important point because if you say, well, David Albert's problem, starts with using that measure, over the state of the universe at the current time, and saying, oh shit. That means that it was closer to equilibrium in the past and the future, and then you have to you have to fix that by inventing the past hypothesis. Well, the wrong step was using that as a probability measure outside of equilibrium in the first place. He dug himself a hole and then jumped in it and then scrambled out. So I think. So I think that, okay, we can assign all, given a state space, we can define all kinds of measures. And if we want to say we're going to take something seriously as a probability measure as an indication of what we should expect, then you have to think hard about what that means. Are we supposed to imagine God choosing initial points according to this measure as a random process, or what?
I mean, it just goes to the foundations of probability theory.
Well, yes.
And I don't really. I mean, if you don't want to be able to count and you don't trust counting measures, then there's no real problem with the error of time in the first place, because you say, well. Okay, our universe is our universe, but we can't really compare that to anything that we think it should have been because we don't have a measure to say how likely it is either way. So then you just deflate the whole problem. And maybe that's a good way out, I don't know. But I guess what I'm saying here is like, okay, maybe the justification for using these measures is that they give you a particular explanatory kind of explanation. So but then you have to be careful not to be circular. You don't want to say this measure solves the error of time, and that's why I want to use it. You need it to be helpful in other situations as well. I think that's the kind of thing that I'm looking for. So, for example, like these descriptions. So the measures come out of a particular description, which happens in the contact system. Okay. These descriptions are also smooth at the Big Bang. I didn't mention it, but it happens to be true. So the Big Bang in these pictures is not a singular point, it's a smooth thing that you continue through. So there's the potential that this description can solve other kinds of problems, and then the whole package together can do something for you. But there's still a lot of work to be done to really say like this is a good program overall, I think. Can I say one more thing? I don't know how much time I have. No. Like, look, one interesting thing that you might ask is like, where does the Liouville measure come from for subsystems? And so you can like, why are these measures not time independent? And the reason is because you always get a time independent measure out of this if there is a simple integral of motion. So, actually, if there's any integral of motion. And that's actually why in cosmology they're very hard to find, because integrals of motion are hard to get in cosmology because everything's coupled to everything else. But once you have subsystems that emerge that become decoupled, they get symmetries, approximate symmetries, you get energy, you get angular momentum. And those integrals of motion allow you to define time-independent measures. So maybe it's like, well, I can't interpret this as any kind of probability measure, but it's useful for describing the system until we get to a point where we have subsystems. That's another possible way out.
I just wanted to add a comment. I want to endorse what you said. So, namely that if we stop thinking that probability is just a matter of counting states, then we undermine the idea that we have any grounds for thinking the early universe is surprising. Yeah. I think that's absolutely correct. And yes, that does undermine a whole literature. Right, it takes the ground, the motivation out of it. But I think that's actually correct.
Okay, Dominic has a finger.
Yeah, I mean, you might just say this is the wrong. You might just say this is the wrong way to go in response to this. But I thought the nice thing about doing this with measures is, apart from, as you said, these gerrymandered measures which you can force to be time independent on the contact geometry, then measure focusing happens to all measures basically.
No, not all measures.
No? How general is the measure focusing? Like?
Yeah. So I don't know.
So you do need to pick particular measures to get.
Yeah. There's a again, I can touch on every single issue, but there's a notion of conventionality in this, in your choice of how you want to describe the system. This drag depends a little bit on the gauge fixing you use to get the dynamic similarity, and there's a conventionality in that. So again, you need to have other reasons to say that this particular system is a useful way to describe. This choice of drag is useful. And so part of what I argue is that there's a whole bunch of other reasons to pick these descriptions, but I don't have time to get into that. Yeah.
That's helpful.
Okay, thanks. Last question.
Hi, thank you for the nice talk. I have actually one clarification to ask, then a question and a quick comment. So the clarification is related to the previous discussion. Since there is dissipation, what's the physical source of that dissipation?
What's the physical source?
Yeah, so you are thinking to cosmology as a subsystem, but within an environment, what that will be?
Yeah, so one way to think about it, the source of the dissipation is that the phase space volume is getting leaked out into the scale factor, which is gauge. Okay, that's the way to think about it in the kind of normal picture where the scale factor is real. On these systems, what's the physical interpretation? Maybe you can think about it as it's effectively that you're getting more and more states that are becoming indiscernible with respect to the overall scale. But yeah, I think that that's a good question actually, and that we have to work on that a little bit better. I'd like to. I mean,
would there be some dependence on at least classically, on the boundary conditions you impose? Because I'm assuming you are like starting with the global system and then like selecting a subset of solution space, and whether the action of the subsystem is open or closed depends on the boundary condition, right?
The spatial boundary conditions, is that what you mean? Yeah, so I mean, yes, it does. It does a little bit depend on the topology. So I pick k equals 0. If you pick k equals 1, then you have to take a subset. Yeah. So with k equals 0, all the solutions have this Janus attractor structure. With k equals 1, only some of them do. Some of them, if you give it the right angular momentum, then you can get recollapse. But I think Faraz knows these conditions better than I do. So there is some dependence, but so the constraints that you put on these models are different from a past hypothesis in the sense that it's not like they're all conditions on like timeless conditions on the parameters. They're not like conditions on the kinds of initial conditions you might have.
And also, so you were starting from the standard description of FW and somehow contactifying it.
Yeah.
But now if I take the latter description as the starting point, I guess your dissipative equations of motion are going to be described by a different action. Can you go back somehow simplifying it?
That's not my work, but David Sloan, my collaborator, has come up with a way to define an action principle. This is stuff, it's called Herglot's action. It's a little bit different. The action contains the value, the Lagrangian contains the value of the action in it. And then you apply the variational principle and you get dissipative equations. It's a kind of old thing, but not that many people know about it. So there is, yeah, you can formulate it as an action principle. There's one way that we could possibly get to quantum theory.
Yeah, because indeed I was going, then the comment was so there is actually a way to quantize quantum manifold, which is essentially, yeah, exploiting the relation between symplectic manifold and quantum manifold. So quantum manifold like projectivization of symplectic manifold, and you can do deformation quantization of that, and this will give you to commutators and dispersion relations. Have you thought about that?
Yes, we're working on it.
Oh,
but I will just talk about more if you have ideas.
I don't, just a curiosity.
Yeah.
Francesca, quick finger.
Well, the finger was just about the fact that suppose we measure that the universe is in fact closed with k equal to 1, so then A is not a gauge anymore, it's the physical scale of the universe. How would you answer to Fabio in that case?
If k is equal to 1, the scale factor is still k, it drops out of the Friedmann equations. You just have k. K is a number, 1. Doesn't have units, so. But yeah, you have to exclude if you want to have the only some solutions will have. Well, it's still a kind of yeah. It's still, what's the word? A positive measure set of solutions will have the Janus attractor structure, but some of them will not.
All right, excellent. Great. So I've seen that lunch is over there. We will continue with the program at 1:45 with the talk by Luca Marchetti until then lunch. Before that, please join me in thanking Sean and Niels.